Hi guys, so welcome to another video. So today we're going to be looking at chapter 5 of the Core Pure Maths 1 module, and we're looking at volumes of revolution. As a prior knowledge check, you could pause the video and have a go at this 3 question. As you know, for prior knowledge we do this so you need to know this basic stuff in order to do this chapter. So for question 1a, 64, b 472 over 5, c 7 over 2. Question 2, 64 over 3, and question 3, 125 over 6. We move on. So we need to be able to calculate the volume of solid created by revolving a shape around the x-axis. So you know how to find area under the curve. Let's say we take a point between A and B, and we want to find this area. So that's just easy, the integration. So now if I say to you, what would happen if I rotate this graph around the x-axis? Okay, then it's going to form a solid. So it's no longer a 2D shape, but we have a 3D shape. So let's have a look at this function. So this is just generic y equal to fx. If I rotate this around, I get a volume. So small increase in the value of x will lead to small increase in the volume of the solid. So if we just magnify this and say we're looking at distance, okay, from x plus delta x. Remember, delta x is a small increment of changes in x. We can label the coordinates here. So this would be x and fx, and this coordinate would be x plus delta x, because we move just a little bit to the right from the x, and then you're changing the x with x plus delta x in the function. So the increase in the volume will be between two values, both of which can be calculated as volume of cylinders. Because we're dealing with small changes, and that's how, when you're working out integration, area under the curve, you're treating each one of these as a rectangle. So you're making it an area of a rectangle by small changes. So that's why as delta tends to infinity, as delta tends to 0, delta x, you're getting closer and closer to the accurate answer. So using the similar terminology here, we could say actually the cylinder, as you make delta x smaller and smaller, would be that volume here from there to there, delta x bit. So volume of cylinder is pi r squared h. Pi r squared, area of a circle, times by h. Because a circle, as you know, is it's a prism, so you times it by h. So from there to there is delta x, and there to there is fx. So we know delta v must be greater than or equal to pi fx squared delta x. And if we take it from there to there, then we know that delta x and then fx plus delta x. So this time delta v is going to be less than or equal to pi fx plus delta x squared delta x. So it's actually between these two values. So there we go. It's between these two values. So now what we could say is if we divide both sides by delta x, we get the following. But make sure that you do the same in the middle, delta v over delta x. So now as delta x tends towards 0, notation changes to d to indicate it's tending towards 0, and you would remember this from the differentiation chapter in the A-level maths. So now what we could say is pi fx squared less than or equal to dv dx less than or equal to pi fx squared. So there is only one logical conclusion here. So dv dx must be pi fx squared, because we've got left hand side and the right hand side of the inequality the same. So there we have it. So to work out volume of solid, we differentiate Okay, so different dv dx would be pi fx squared. Now, integration of both sides with respect to x, and this will be from your differential equation from your A-level maths. When you separate the variable, v would equal to integral pi fx squared dx. So there we have it. If we differentiate v with respect to x, we get dv dx. So therefore, if we integrate dv dx with respect to x, we get v. And there we have it. So this is the formula we're going to use to work out volume of solids. And since pi is a constant, you could just take a factor of pi out. So you will see on some formula books it's actually written like this with pi outside. And a and b are your limits. So this would be the formula you see in the formula book. And another way you could rewrite this is pi integral y squared dx, because sometimes they're written as an equation rather than a function. So there's okay, so here's an example. We have a diagram with the graph y equal to 9 minus x squared. What we want to do, we want to rotate this graph around the x-axis by 360 degrees and find the exact volume of the solid generated. So the word exact here, so we need to be careful that we don't start giving to decimals. So we need to find the intersection first. So we need to get the limits of a and b. Well, a we know is going to be just 0. So b, we set y equal to 0. And that gives us this x value. So x equals to 3 or minus 3. And since we're only looking at the right hand side, we know clearly x is going to be 3. So now, if we use this formula, our upper limit is 3, lower limit is 0, or y is the equation 9 minus x squared, all squared. So now if we square the bracket, make sure you use FOIL and you expand this, and then we could start integrating, and we'll use the limits 3 and 0. We subtract one from the other, and that will give us the exact volume. Notice it said exact volume, so we're going to leave it in terms of pi and not substitute that in. Alright, so here's an exam question from the old A-level paper. You guys pause the video and have a go at this. It's a 5-mark question, so give yourself about 5 minutes. So it's actually 4,236 pi over 5, which is in exact form, and the question did say to live in that form, so very good. Now that we know how to rotate around the x-axis, we could do the same thing but rotate around the y-axis. So we know how to work out area when it's a function in terms of x, you make it in terms of x. So here we want to rotate around the y-axis. So this will look something like this. So there's nothing particularly new here. Rather than having y squared, we're going to rearrange the formula and have it in terms of x. So when we're rotating on the y-axis, we put pi integral x squared dy, because we're rotating on the y-axis. So here's the question. You guys pause the video and have a go at this. So the first thing here, we want to make it in terms of x. If we square both sides, y squared plus 1 is equal to x. If we substitute in here, we want to square that, because it's x squared. So you square that by using FOIL method, you expand the bracket, and then you start to integrate. Here we integrate with respect to y. Make sure you write dy and not dx. And the limits here were given on the y value. So be careful, sometimes you'll be just given the x value. In that case, you just substitute into the equation here to find out the y value and so on. So here it's a straightforward substitution. You substitute that in, and that will give you the volume. So here's another question, and let's pause the video and have a look at this. Yep, so it's 77155 over 14. So here, again, we're making x a subject and then squaring the x, and that gives you the solution. So there you go, guys. So you know how to work out the volume of solid, both in terms of rotating around the x-axis and the y-axis. So if a part of a solid of a revolution is a cylinder or a cone, you can either work out the volume respectively using cylinder pi r squared h, cone third pi r squared h. So if we take these 2 points here, and this is our height, and this would be our radius, okay, a cylinder can be formed by starting with a horizontal line and rotating it around the x-axis like that. Yeah. Now a cone can be formed if you have a line coming down like this, and if you rotate that around the y-axis, you could form a cone. So here, this would be the height and this would be the radius. So let's have a look at this question here. It says the region R is bounded by the curve with the equation y equal to x cubed plus 2, and the line y equal to 5 minus 2x, and the x-axis and the y-axis. It says verify that the coordinates of A are 1, 3. A solid is generated by rotating the region 360 about the x-axis. We're going to find the volume of the solid. So if we sketch this, just give an idea what we're looking for. So we know a cubic graph looks like this, and the y-intercept is 2. And then we have a straight line with a negative gradient and y-intercept of 5. So we should be able to, at this point, sketch graphs, this kind of basic graph. So the region we're interested in is this region here. So now, if you substitute x equal to 1 in both equations, you get 3 for y. So if we substitute into the curve, we get 3. If we substitute into the line, we get 3. So we verify the coordinates of A is indeed 1 and 3. So here's the more interesting bit. We want to work out the volume. So for this, we could split the area into 2 parts and find both separately. So we could work out from 0 to 1 and 1 to 2.5. So if we call that R1 and call this R2, so the volume of revolution for R1, so if we work out the volume of R1, we're only focusing on the cubic graph. So if we square the cubic graph and multiply by pi once we substitute in the limits, as the exact form, we get 36 pi over 7. Now if we same thing for R2, at this time the volume is coming from this triangle. You could just use the formula for volume of cone, which is third pi r squared h, or you could use integration. Both methods will give you exactly the same result. So now we've got the volume of both of them. We simply just add this, the answer will be 135 pi over 14. So here we could see it's quite an interesting graph. We've got a square root of x graph, and we've got 1 over 8x. We've got a reciprocal and this graph. And it makes an interesting area here. So the first thing we want to do, we could just, to find where they intersect, we could just substitute one into the other, because y equals to y equal to. And then if we solve for this, we could work out the x value, which is just a quarter. And we knew it had to be less than 1, because 1 is here. So now, if we think about the volume, we could work out this area first. So now if we work out the R3, we work out the area of the one minus the area of the other, we could work out the volume afterwards. Or there's another way we could do this. Because the limits are the same, we can subtract before any integration. So you could just do y2 squared minus y1 squared. y2 and y1, this is the equation, root x and 1 over 8x. So we could square each one of these, and then we could think about the integration, put the limits in, and this will give us the volume. Okay, so here's another interesting graph. So what I want you to do is just pause the video and work out the volume of revolution of this one. So once you substitute this in, work out the area rotated around with your volume 4, 5, or 15. Okay, so let's have a look at this question here. So they say manufacturer wants to cast a prototype for a new design for a pen barrel made out of solid resin. The shady region shown in the diagram uses model for the cross section of the pen barrel. The region is bounded by the x-axis and the curve with the equation y equal to k minus 100x squared, and will be rotated around the y-axis. Each unit on the coordinate axis represents 1 centimeter. So we can see on the diagram what it looks like. We want to suggest a suitable model for value of k. We want to also use our value of k to estimate the volume needed to make this prototype, and also state one limitation of this model. So most pens are around 10 to 15 centimeter long, so anything in this range would be sensible. If you didn't know, well, now you know, 10 to 15 centimeter long. So we could say 10, that would be one suitable value. So y would equal to 10 minus 100x squared. Note that we are rotating about the y-axis, and the horizontal limits will be 0 and 10. So if we're rotating around the y-axis, we need to do pi x squared dy. So what we need to do, we need to go back to our equation and make x the subject of the formula. And then once you make x subject of the formula, you square it. So that's same as just saying x squared. So you don't really need to root it because you're going to be squaring afterwards. And now you just simply substitute that in and work out the volume of revolution around the y-axis. So once we work that out, do our calculation, because we rotate around the y-axis, we have in terms of y, and we'll get half pi. Okay, so we want to state one limitation of this model. So one of the limitations, we could say, it's unlikely that the cross-section of the pen will match the curve exactly. The pen might have other parts that would affect the shape, etc. So it's very open, this question.